It could be manipulated. And the ground rules that were proposed still exist. And in fact, all the work that we do on this campus, the vet school ourselves, and others throughout the country are framed under these particular rules. What about actually making genetically engineered organisms? Well, this was one of the first. The plant there is a tobacco plant, and it contains in every cell luciferase. Luciferase is from the firefly, and it's what makes a firefly produce light. And this particular plant was engineered so that it could produce light. Why did they do it? Well, it meant that you could grow rows of trees and take down all the street lights. That was the first thing. The second thing was people like me spend the week before Christmas trying to fix the lights on the Christmas tree. You don't need to do that. You just produce a GM Christmas tree which has got different colours. There was no commercial advantage to producing that particular plant, but it demonstrated that when you engineer using genetic manipulation, you actually change every cell, and that was key because it meant that you could then transfer that particular characteristic to subsequent generations. Probably the first commercially important GM crop was this one, the tomato. And I'll tell you more about this later. That was 1994, and that work was actually done, although not with the Flavour Saver, it was done here. It was actually done in North Lab. Don Grierson, who many of you will know, Don and his team actually made the first genetically engineered plant that had commercial opportunities. Okay, so that's a little bit about the history, but what might we do? We've got this technology, how could we use it? Well, I need to say at the outset, this has not been done, and even showing this particular slide is going to make some people very anxious. It's not been done, it's just to show you how you could use the technology. Now, I don't know how many of you grow tomatoes. We grow tomatoes in our greenhouse at home, and there are two things that happen with tomatoes. One is they produce loads and loads of green fruit, which never ripen. But they do ripen if you go on holiday, or they do ripen the day after you have your first low temperature of the year and the plants drop dead. So tomato plants are very sensitive to cold. Temperature drops to about 10 degrees or a little bit lower, and they die. Which is ironic, really, because the tomato originally came from the Andes and actually grows under cold conditions. But the commercial tomato has lost that capacity. So let's say we want to make a tomato plant which is able to tolerate the cold. How could we do it? Well, first thing, let's find an organism which can tolerate the cold. Well, this is a good one. The flounder. The flounder, actually, by its name, lives at the bottom of the seas, the oceans, and it can tolerate the cold. And therefore, you would imagine there must be some gene or gene complex which allows it to do that. Let's suggest there's a single gene, and let's suggest it actually produces something like antifreeze. If we could identify that gene, let's say we could somehow take it out. This has not been done, in case you suddenly think that all your tomatoes have got fish in them. They haven't. So what you do is you take that piece of DNA out and you need to put it into a bacterium, and then you take your bacterium and you somehow engineer the tomato plants. And you can do that now pretty easily. And once you've done that, you then will have a tomato plant which contains that gene, which is going to make that antifreeze, and therefore the plant will be resistant to the cold. Not been done. There are ethical reasons why people might not wish to do it. It's not something that technically one will be able to do very easily anyway, because I'm sure there isn't a single gene. But it just gives you an idea how you could potentially change something and make it better. What has been done? Well, these are some of the things that have been achieved and we can talk a little bit about them. Most of these are what we call first generation GM crops. These are plants which are resistant to simple traits, or they have particular characteristics. They're resistant to herbicides. It may not be immediately clear why that would be advantageous, but we can unravel that in a moment. They're resistant to insects. Clearly that would be advantageous, a plant that could actually protect itself. Resistant to viruses. Some of you may not have been aware how plants were attacked by viruses, just as we are, and we lose a lot of a crop as a result of virus infection. I think there's a conspiracy to make as much noise as possible by bashing pipes and doing the washing up. Let's talk about the first one of those, herbicide resistance. This is a relatively old slide now, and this is of tomato plants. The one on the right has been sprayed with a herbicide and looks really quite ill. The one on the left has been sprayed with the same herbicide and looks fine. Why? Because the one on the left has got within it chemistry which has been the result of genetic engineering, so that that herbicide is actually broken down, so the herbicide doesn't kill the plant. Why could that be useful? Well, imagine that you are a farmer and you're growing your crop and you're growing it in an area where the crop and loads of weeds are going to come together. You can't spray the weeds because you'll kill the crop. But if the crop is resistant to that herbicide, you can then go in and you can potentially clear up those weeds which don't have that resistance. And you can see the difference. And this can be valuable because it can mean that potentially those plants produce a yield which they might otherwise not. That's herbicide resistance. What about insect resistance? Well, here we've got on the left a tobacco plant which is resistant to a particular insect. There's a caterpillar you can probably just see in the middle. On the right hand side you've actually got a plant which hasn't got that resistance. If we move the slide on for a bit, this is what we end up with. This is our crop which isn't resistant. In case you're not sure which is which here, that's the plant, that's the caterpillar. And if you're a smoker, and I'm sure none of us are, but if you were, the best thing to do is smoke the caterpillar because there isn't actually tobacco left. So you can see that there could be advantages there in having a plant that is resistant to a particular pest. Well, tobacco may be not something which is key, but this is a key crop. This is corn, and what we've got here is a picture on the left of corn which is resistant to the corn borer, and on the right, one that isn't. The crop on the left has been genetically engineered. It produces a toxin, so the corn borer dies. You don't, the birds don't, but the corn borer, sadly, if I had my way, I'd pick them all off and I'd relocate them somewhere else. But sadly, that probably isn't going to happen. And therefore, this is one way of resolving the problem. So the crop on the right has fallen over. Why has it done that? The corn borer lives up to its name. It gets into the stem, it bores holes, makes the stem weak, and it falls over. Whereas on the left-hand side, there's no attack. So you can see that in terms of yield, potentially you're going to get a difference between those two crops. Now those are things that have been done and things that work, and they work very effectively. But it's not just changing yield, you can potentially change the quality of different products. And I want to just talk a little bit about this. Shelf life. Shelf life is very important. At this time of year particularly, I go into Sainsbury's, and some of you will have seen me because I'm there with my long sheet of paper trying to work out where things are and then putting things in other people's baskets. I don't know why I always do that. And you think it would be really nice to have an apricot. But you can't buy an apricot, you have to buy a punnet of 20.